Okay, so we're starting chapter 20, nuclear chemistry. Up until now, all of the reactions we've been talking about have been chemical reactions. And nuclear reactions are really a totally different sort. So we've got a table here, 20.1, that compares chemical versus nuclear reactions. So chemical reactions will involve electrons either being shared or transferred, forming bonds, forming ions through the addition or removal of electrons. It's all about electrons. Nuclear reactions involve protons and neutrons, the other subatomic particles, and they really have nothing to do with electrons at all. Chemical reactions will not change the atomic number or the elemental identity of any atoms. Nuclear reactions actually change atomic numbers. You can transmute one element into another element, which is really interesting. Chemical reactions are really agnostic to different isotopes. Carbon-12 will react chemically in pretty much exactly the same way as a carbon-13 or a carbon-14. The isotopes are just kind of irrelevant to chemistry. In nuclear reactions, isotopes are paramount. What isotope you have is going to govern what sorts of nuclear reactions can occur. And then in chemical reactions, we have conservation of mass in a very straightforward sense. The mass of all of your products is going to equal the mass of all of your reactants. In a nuclear reaction, that's not necessarily the case. And it's simply because of Einstein's equation that E equals mc squared. This relates energy and mass, and it's just because nuclear reactions can involve such a dramatic change in energy that manifests as a change in the observed mass. And so nuclear reactions are really quite different. The nuclear reactions do realize the alchemist's dream of transmuting one element into another. For thousands of years, most of human history, people had hoped to find some way of converting useless starting materials into precious ones, like changing lead into gold. Well, nuclear reactions will actually... Oh, sorry, let me back up a bit. Dalton's atomic theory kind of stated that those sorts of transmutations were impossible, that no chemical reaction was going to change one element into another. And that's true about chemical reactions. But nuclear reactions actually do change one element into another. Unfortunately for the alchemists, they only do so within very rigid, strict rules. And actually lead ends up being a product of reaction more than a reactant. You can't change lead into gold through nuclear chemistry. Not in any of the sorts of reactions that we're going to talk about today. An interesting thing about nuclear chemistry is it involves changes within the nucleus of the atom. And you may recall, going back to our atomic structure section in Chemistry 1210, that the nucleus is a teeny tiny fraction of the total volume of an atom. It is right in the center, and it is surrounded by at least one, sometimes many layers of electrons. It's sequestered down there inside the electron shell. And because of that, external conditions don't really affect nuclear reactions very much. If you raise the temperature or lower the temperature, that doesn't affect the reaction rate. If you have a radioactive nucleus, like say carbon-14, and it's a part of graphite, pure carbon, or if it's a part of carbon dioxide, a very oxidized form of carbon, or methane, a highly reduced form of carbon, none of that matters. Carbon-14 will decay in the same way at exactly the same rate, regardless of any sort of an influence we might try to exert over it. in ways that normal chemical reactions can be influenced. So I like to say that the nuclei are sequestered inside their hermitage with electron walls, and they're going to behave in the same way regardless of the chemical context of what that atom is in or the environmental conditions. So one other quick little bit of vocabulary, and then we'll dive into nuclear chemistry. So we've been talking about isotopes. So an isotope is, isotopes are the different forms of an atom that have different numbers of neutrons. Carbon-12 has 6 protons, 6 neutrons. Carbon-13 has 6 protons, 7 neutrons. Carbon-14 has 6 protons and 8 neutrons. Those are different isotopes of carbon. Technically, an isotope is the entire atom that would include the electrons. So there would be 6 electrons around each of the different isotopes of carbon. A nuclide, or should it be nuclide? I'm actually not sure. Sorry, double checking your book. Either a nuclide or a nuclide is referring to just the nucleus. And so a carbon-12 nuclide is the 6 protons with the 6 neutrons and no electrons, or the number of electrons is irrelevant, whether it's positively charged or negatively charged. The nuclide refers only to the nucleus, and that's where everything happens. So I don't really care about the difference between these two. I will probably use them interchangeably in my lectures, but there is a small pedantic difference between them, where this explicitly refers to only the nucleus, and this explicitly refers to the entire atom, including electrons. Okay, so isotopes which spontaneously undergo nuclear decay are called radioactive, or they're called radioisotopes. And not all isotopes of an element are radioactive. You can take a perfectly fine element like hydrogen, which is stable. It's the oldest element in the cosmos that started near the Big Bang, right? And they've been around for a really long time, and so we know they are stable. They are not radioactive. But there are different isotopes of hydrogen, like deuterium and tritium, that have more neutrons and actually are radioactive. And so it's the isotope itself that we'll talk about as being radioactive. In other words, hydrogen isn't radioactive, but tritium, the isotope of hydrogen with 2 neutrons, is radioactive. Nuclear radiation is the energy and matter that is cast off in the course of a nuclear reaction. And there are 4 different types of radiation that we're going to be talking about today, and 5 different types of radioactive decay. So the first is called alpha radiation. So alpha radiation is going to send off what we call an alpha particle. So that's the Greek letter alpha. It looks like a pretentious lowercase a. And it has a mass number of 4 and a atomic number of 2. This is simply a helium nucleus, right? Helium's the second element, has 2 neutrons, 2 protons. An alpha particle is a helium nucleus that is ejected at high speeds. And so with a mass number of 2 and a 2 protons, that means it has a charge of 2+. But usually when we're talking about nuclear chemistry, instead of writing the charge up here, we let this, the atomic number, sort of represent the charge. Of course, the number of protons is going to be the magnitude of positive charge. And the electrons are usually not going to be a factor in balancing our nuclear reactions, and so we don't need to worry about them. Anyway, So this is an alpha particle. Alpha particles are able to penetrate the least far of all the different types of radiation. A thin sheet of paper would effectively stop an alpha particle. And so as far as, you know, the danger of alpha radiation, while it certainly can be dangerous if you're unprotected, simply encasing a source of alpha radiation in a box or plastic would actually block that radiation. Okay, then we have beta decay. And a beta particle, here's the Greek letter beta, and that looks like a pretentious uppercase B. A beta particle has no mass. Now, it doesn't technically have zero mass, but the mass is very, very small, and its charge is -1. So a beta particle is actually just an electron. Actually, I'll write that right here. You know, this is a helium 2+. That is what an alpha particle is, and beta decay is simply an electron, again, that is ejected at high velocity. And so beta particles are able to penetrate further than alpha particles. If you go in for an X-ray or something, you'll wear apron with lead impregnated in it. So, you know, a thick layer of lead would protect you from a beta particle very effectively. So beta particle is just an electron. You'll notice we put in the lower left corner here a -1, sort of like an atomic number, but in this case what we really just need to keep track of is that it has a -1 charge. Then there's a positron. So a positron is represented with the beta, but we put a +1 and a 0. And so a positron is actually the antiparticle to the electron. You've perhaps heard of antimatter. And this isn't a physics class, so we won't get into antimatter. I frankly don't know much about it myself. But in antimatter, every ordinary matter particle has its antimatter complement, and the charge is reversed. And so a positron, you could represent it as an E with a plus or as a P with a plus, but the P plus is confusing when you consider that could represent a proton. And so even though it's called a positron, we really are going to kind of stick with either the E with a plus or the beta with +1. That's a positron. And then finally, gamma emission. So a gamma radiation has no mass and no charge, and a gamma ray is simply a high energy photon. So it's light. And you may recall the electromagnetic spectrum, how everything from radio waves to microwaves to infrared to visible light and ultraviolet light and X-rays, those are all kind of the same thing. They're all photons of light, whatever light is. And gamma would be the next one after X-ray. So these are extremely high frequency, extremely short wavelength photons of light. And gamma rays can either penetrate not very far, on the order of like alpha particles or beta particles if they're on the low energy side, or they can penetrate through even lead if you're on the, depending on the energy of the gamma rays. And so gamma rays are pretty diverse. It's really a whole region of the electromagnetic spectrum. Okay, so we'll be using these symbols right here as we're balancing nuclear reactions. So you should be familiar with them. Now, each reaction is going to have some radioactive isotope, so we could call it a radioisotope or a radionuclide, that is the reactant, and that is called the parent isotope or the parent nuclide. And then it's going to emit some form of radiation, alpha particle, beta particle, gamma ray, positron, but it'll also leave behind a daughter isotope or a daughter nuclide, which is going to be different. And we'll see how that works with the different types of decay. So let's first do alpha decay. So in alpha decay, the radionuclide will eject an alpha particle, and what is left behind afterward will have a mass that is smaller by 4, that's the mass of the alpha particle, and will have an atomic number that is smaller by 2, because there are 2 protons that make up the alpha particle. So you can balance alpha decay just by balancing that mass number and the mass number and the proton number. So let's look at an isotope which decays via alpha decay, something like uranium-238. So there's U-238, and we're going to go ahead and put the atomic number 92 down there because that's going to help us in balancing. So U-238 is going to decay into some daughter isotope plus an alpha particle. The alpha particle has 4 and 2. So what is the daughter isotope? Well, I know that the sum of the masses on the product side are going to have to equal the mass on the reactant side. So 4 plus X is equal to 238. We'll call that 234. And then the sum of the charge or the proton number on the bottom here for the product side is going to have to equal the sum on the reactant side. We've got 92 over here, we've got 2 over there, and so it must be 90. And now, what is element 90? Well, I don't have it memorized. I don't expect you to either. So we'll look at a periodic table here. Let's see. Lead's 82, polonium's 84. Oh, you know what I should do? I should find uranium. There it is, 92, and just go down 2 positions. Thorium is 90. So I'll put a TH. Thorium. And let's get rid of that periodic table. Okay, so you see 234 plus 4 equals 238. 90 plus 2 equals 92. And alpha decay will always take an element and transmute it into the element that's 2 positions below it on the periodic table. Let's look at another form of decay. Beta decay. So a beta decay is going to convert a neutron into a proton and eject a new electron. So it's like the neutron breaks apart and forms a proton and an electron. The proton remains in the nucleus and the electron is ejected as a beta particle. And I want to pause a moment and say this seems to imply that a neutron is simply composed of a proton and an electron stuck together. That model doesn't actually work very well. We'll see with the next type of radioactive decay, positron emission, how that model doesn't really hold water. So what is a neutron and what is its relationship to protons and electrons? Well, ask a physicist. Okay, so I kind of have a very surface understanding of what they call the standard model of particle physics. It has to do with quarks, which are the things that make up things like protons and neutrons, but electrons aren't made up of quarks, and so I still don't even really know how beta decay really works, how electron capture and positron emission, which we'll look at later, really works. The physicists do have a good understanding of this. I don't want to suggest that we as a scientific body are ignorant about this. It's just I personally am ignorant about it. And so I recommend going and talking to one of our excellent physicists and getting their take on, on beta decay and just how is it that a neutron can convert into a proton plus an electron. Anyway, so let's balance the beta decay of an isotope of tellurium. So 210-81 tellurium is going to decay via beta decay. So it's going to emit a beta particle. I should have given myself more room, but I'll just try to write really small. And we'll do the same sort of balancing. So the mass on the right should match the mass on the left. That'll be 210. And then the atomic number, or the number of protons on the left, should sort of match the number on the right. Well, here we have a -1, and so in order to make that match 81, we're going to need 82. So let's pull up the periodic table again. And here is, oh, sorry, that's not tellurium, that's thallium. So that TL is thallium, element 81, and we'll look at the one just right above it. That's lead, is 82. So we'll put a lead right there. Lead is 82. Okay, and that is beta decay. Again, just add these numbers up and they'll equal that. Add these numbers up and they'll equal that. So you can always find the daughter nuclide as long as you know the parent nuclide and the type of radiation it undergoes. Okay. Sorry, let me really quickly get my notes in the right position. Okay, so right there I have a practice problem for you. 234 thorium, 234-90 thorium is going to decay to produce 234-91 Pa, which I believe is protactinium. So what decay process is involved? We can do the same sort of balancing that we were doing before, only this time we're trying to find what type of radiation is released in this decay process. So 234, that means whatever radiation is emitted is going to have 0 mass. And then 90 here and 91 there, well, that's going to be a -1. This must be beta decay. Protactinium is one position up on the periodic table from thorium, so that's a signal that it's going to be beta decay. All right. Get rid of that. So the next type of radioactive decay is gamma decay. And it should be noted that most radioactive reactions will emit a gamma particle. We'll leave it off though, unless it's particularly important to us at that time. But there are some reactions which emit only a gamma particle, or only a gamma ray. And so gamma decay, when we talk about gamma decay, what we usually mean are those special reactions that don't emit an alpha particle, beta particle, positron, or anything else. All they do is release the gamma particle, or the gamma ray. And so here's an example of that. So, where are we? Tin, 119 tin can undergo gamma decay. The gamma ray has 0 mass and 0 charge, so what is left over? Well, it's still 11950 tin. So what's changed? It's still tin, but it has lost a large amount of energy when it emitted that gamma ray. And what has changed is the internal configuration of the nucleus. It's not something that we have an easy way to represent or predict, but if you have tin that is in a nuclear excited state, then it will release that gamma particle or the gamma ray as it relaxes back down to the ground state. And I apologize, I keep saying gamma particle. Technically it's a ray because a photon has no mass, so I should be calling it a gamma ray. So tin's not the only one that does this. There is an element called hafnium, and one of its isotopes is kind of particularly efficient at absorbing energy, storing it in an excited nuclear state, and then releasing that energy later in the form of gamma radiation. And it's kind of been proposed that we might take a sample of this hafnium, stick it in like a nuclear reactor where it can be bombarded with gamma rays that are a result of that nuclear process, and make this hafnium sample charged into its excited state. And then you can take that hafnium sample out, and it will kind of hold that energy and slowly release it over time, so you could sort of transport it somewhere else and use the energy in another place, or use that energy over a long period of time as it slowly releases its energy. It's kind of like a battery that is recharged by sticking it in a nuclear reactor, and then will slowly release its energy over time through gamma decay. Anyway, it's kind of a fun idea. I'm not aware of it actually being carried out in any practical sense, but it's sort of rechargeable is the key point. You would still have tin after this reaction. You would still have hafnium after that reaction, and so it's like a rechargeable nuclear battery, which is kind of a cool idea. Okay. There we go. Next is positron emission. And again, a positron is like the antiparticle of an electron. Positron emission is going to convert a proton into a neutron, and it'll emit a positron in that process. And so fluorine-18 is an example of an isotope which will undergo positron emission. So 18F9. And it's going to emit that positron. And what will be the daughter isotope or the daughter nuclide? Well, it'll still have a mass of 18 because the positron has 0 mass. But the atomic number here will have to be reduced by 1. So 8 plus 1 equals 9. And that is an oxygen. So oxygen 18 is the daughter nuclide for this positron emission process. It's the same mass, but one position down on the periodic table, which is kind of the opposite of beta decay, which is the same mass, but one position up on the periodic table. And then we have a kind of strange sort of radiation called electron capture. In electron capture, one of the core electrons of an element are actually absorbed by a proton in the nucleus, and that converts into a neutron. And so in this case, you'll actually have an electron as the reactant. So carbon-11 will undergo electron capture. So 11,6 carbon. And here we'll have the electron 0, -1 as a reactant. And what will be the product? It will still be 11, but now instead of 6, it will be 5. 6 plus a -1, that's going to equal 5. So that's, hold on, that's boron. Carbon-11 will convert to boron through electron capture. And you'll notice the product here is one position down on the periodic table. So positron emission and electron capture will both produce the same daughter nuclide or daughter isotope, but we can tell the difference because one of them emits a positron that we can detect, and the other one does not. Electron capture does not. So, let me really quickly give you another practice problem. There we are. Okay, so you can see it down there, 4019 potassium will decay into 4018 argon plus some radiation particle. I don't want to give it away. So what decay process is involved here? Well, we can see that potassium and argon are neighbors on the periodic table, but argon is one position lower. So this is either electron capture or positron emission. But the fact that we're emitting some sort of radioactive particle that we can detect tells us that it must be positron emission. Okay. Now, sometimes the daughter nuclei of a radioactive reaction are themselves also radioactive. You might have noticed that our uranium-238 decayed into thorium, and thorium at some point decayed into, where was it? Oh no, that was thallium. Oh yeah, sorry, thorium decayed into protactinium. I apologize. So thorium is the product of U-238 decay, but it can also decay itself into protactinium, and that was the 234 isotope of thorium that we were talking about in the context of alpha decay. And then protactinium is also itself radioactive, and so sometimes you can have these radioactive reactions that daisy chain onto each other, one after the other, after the other, after the other, until finally they settle onto some stable isotope. And that chain of reactions is called a radioactive series. So let me, I need to jump forward a bunch on the slideshow. Sorry, it's hard to get everything working perfectly smoothly. I believe this is going to do it. Okay, so this is the radioactive decay series for uranium-238. On our x-axis we have the mass number, and on the y-axis we have the atomic number. And so alpha decay is going to go down and to the left diagonally. Beta decay, which keeps the same mass number but increases the atomic number, is going to jump upward. And you can see that uranium-238, when it decays, it starts quite an impressive chain of different radioactive processes. One alpha decay followed by a beta decay followed by, what is that, 4 or 5 alpha decays followed by one beta decay. At that point you have an isotope of bismuth that can undergo both alpha and beta decay. Those two pathways later reconverge, and at the end of the line you end up with lead. We saw lead earlier as the product of thallium beta decay. And lead will actually show up as a sort of an interesting element with respect to nuclear chemistry in the next section. Especially these larger elements, uranium, plutonium, neptunium, americium, a lot of these larger elements are going to decay not just once, but they will set off a whole radioactive series. Because the large elements are for the large part unstable, and it's going to take more than one step before they get down to the stable smaller elements. It's going to each alpha decay or beta decay event is just inching it a little bit closer to stability, and that's the whole topic of 20.2. So I'll stop myself there and not go on. Okay, so there's one last quick little thing. How do we measure radioactivity? So first of all, activity is sort of a catch-all phrase for the strength of radiation, whether it's alpha decay or beta decay or positron emission. And what it is disintegrations per unit time. The disintegration is just radioactive decay event. And so activity is kind of general, but we have an SI unit of activity, that is the becquerel. I need to make sure I spell this correctly. BECQUEREL. So the becquerel is the SI unit for radioactivity. And 1 becquerel is defined as 1 disintegration per second. So that's the SI unit, but becquerel is actually a very tiny amount of radiation for most of the radioactive elements that we like to look at in chemistry. So instead we have the Curie. Named after the French physicist Marie Curie, and she studied radioactivity. She's a really interesting person to study or read a biography on or whatever. So Madame Curie invented this unit, the Curie, or it was named after her anyway. I don't know if she invented it. The Curie is equal to 3.7 times 10 to the 10th becquerels. So the Curie is much larger than a becquerel. It's about 37 billion becquerels, and that's more like if you're I don't know, visiting the Chernobyl nuclear reaction disaster site. If you were to open up the sarcophagus and go into the nuclear reaction chamber, you would be measuring, tens of billions of disintegrations per second. That's an impressive amount of radiation compared to the measly little becquerel. So a Geiger counter is the instrument that we use to measure radioactivity. Hold on a second, I'm pulling up a slide that shows how a Geiger counter works. There it is. And basically it just has a gas chamber where the gas is easily ionized by radiation. So it's a gas particle, like maybe a noble gas or something, that's not going to undergo a chemical reaction, but when a radioactive particle collides with it, it'll lose an electron. And then that gas is placed in a chamber with a strong electric potential. There's a positive side and a negative side, and once it loses that electron and becomes positively charged, it will careen toward the positive side, and it'll impact with enough energy that we can detect as an electrical current. And so Geiger counters, you've seen them, I'm sure, in like TV shows and movies. They're the little things that make the clicky noises, and each click represents a single detected disintegration event. You can also, if you want to be less dramatic and more quantitative, you can have the Geiger counter indicate the disintegrations per second with a needle, or even record that data digitally. And so Geiger counters are kind of ubiquitous. I'm sure you've heard of them or seen them, but that's how they work. And then one last little bit before we're done with this section. Sorry, there's kind of some interesting applications of radioactivity. Actually, two little bits. First is that smoke detectors actually use an alpha decay to detect smoke. The idea is alpha particles are stopped so easily, so readily, that just having a veil of smoke between the alpha particle source and the detector would be enough to block the alpha particles. And so a smoke detector has an alpha particle emitter that is constantly emitting alpha particles, and they're being detected, and if that stream of alpha particles is ever interrupted, then it'll go off and indicate that there is smoke. Smoke detectors technically should be disposed of properly because there is a radioactive alpha particle source inside there. It's teeny tiny, but you should dispose of it properly, and you really should be careful not to, say, disassemble your smoke detector and take apart all of its components and try to go hunting for that alpha particle source without a protective covering. Even alpha particles can be dangerous. Okay, and then the other is using radioisotopes as tracers. So in medical imaging, for example, you can inject a sample in somebody's blood or into their food or whatever that contains radioactive isotopes like iodine, or I think cobalt is used as a radioisotope in medicine. And the idea is that we can actually see the flow of these elements through the body using radioisotope telemetry, using detectors that can figure out where the radioisotopes are in your body and actually map them out. So this is a medical imaging technique. I believe it's called a PET scan, positron emission tomology is at least one of those methods. And then you can also use radioisotopes as tracers in a bit more of an abstract sense. If you wanted to figure out how a reaction proceeds, you might tag or mark one of the reactants with radioisotopes that you've specially prepared. And it doesn't even have to be a radioisotope. It could be a stable isotope as long as you're able to separate them after the fact. Using different isotopes, let's say you wanted to know how hydrogens get moved around in the course of a reaction. You might have one of your reactants with a lot of deuterium in it, and then you look at your product and see, oh, well, where are the hydrogens, regular isotopes of hydrogen, and where are the isotopes of deuterium? And that can give you an insight into how the reaction mechanism proceeds. Okay, I better stop it there.